All right, we're back for some more here. I found something from a little blast from the past here, Winter 16. This thing has it all almost. The only questions it doesn't have are the two questions about termination steps, which if you look over the last three fourth exams, like test 4, the last 3, you'll see it's the same answer every time for parts G and H, which aren't here. So I'm not going to go over those. We'll go over how to do this. And this is about as hard as it gets right here. This one little point here is it's a point that takes the most thought forever for one point. So let's break it down. Forming hydrogen bonded to a halogen happens in propagation step 1. And the more negative that is, the faster it is. We can get rid of half the products based on that. Forming H bonded to I versus forming H bonded to Br is the two things here. So we got part 1. HBr formation versus HI. The more negative the formation of that bond in terms of delta H, the faster the reaction. You will read that during chapter 8 and look at it on all the exams. How do we decide such things? Well, we got to go find the exam. And I have it over here. I will bring that over to this screen here. I'm trying. There, it happened. All right. We need our BDE table, which is right at the beginning. And there it is. No, where is it? I saw it 10 seconds ago. I grabbed the wrong exam, I think. Winter 16, test 4. I swear I saw it. Can't do the question without it. That's test 3. I see right there. No wonder it's not there. I grabbed the wrong screen, that's all. And there it is. Sorry about that. Computer's trying to keep up. There we go. Can we rotate this? I'm not used to, I'm doing it from Firefox. I'm not used to it, but that seems to do it. Apparently not. Reading sideways, we see that H bonded to Br, this is how much energy it takes to break that bond. Positive 368 kilojoules must be put in to pop that bond open. When you form the bond, it's exothermic to the tune of negative 368 kilojoules. And yes, the anticipation of HI is a lot less exothermic. We have negative 297 versus negative 368. We have the answer to our question. Negative 368. Just going to close that window. HBr negative 368 versus, I think it was negative 297. Correct me if I'm wrong. Doesn't really matter. We made up our mind with a much more negative. That's faster. So because of that, we're crossing off every possible product that has HI in it. Question 2, we'll do in green. Oh, I got some green up there. It's ignoring me. 2. We have to ask the question, which carbon-hydrogen bond CH breaks faster? Which CH breaks faster? Clearly, one of the products has this H being broken. That would be this product here. And you might be surprised to hear that let's see. Oh, that's tricky. I want to point something out. These two purple H's, they are identical. There is no distinguishing this from this. Didn't lose anybody there, I hope. This product comes from loss of this H to make a radical here, and the iodine goes there. That would be the same story as losing this H. But if you lose this H here and put a radical there, you might be confused to hear this, but that will make this product. What? How the heck? There's no iodine up here. Well, if you make a radical here, the special thing about that radical is not that it's secondary, that's a little special, but it's allylic. Allylic means it's one away from an alkene. It's on a carbon, one away from an alkene. That's called an allylic carbon. They're very special. They can resonate with the alkene. You can move the radical to in the middle to make half a pi and the pi to make half a pi, leaving behind a radical there. And that would put the iodine there. So this gives products, we'll call this one 4 and 6. And this one gives, they are both the same energy though. And 4 after resonance. Our mechanism will show that. And how do you find the energy for these two CH bonds? It's all about categories. Secondary allylic is the full name of the category. Do not skip the allylic part. You will find the wrong number. We do not want to find the wrong number. All right, so the carbon hydrogens are all here. The allylics start here. This is a carbon, one away from an alkene carbon. That's an allylic carbon. It's primary allylic. So these are allylics. I can't write on that screen, sorry. This is primary allylic. Secondary allylic is the one I need. Why is it allylic? It's on a carbon, one away from an alkene. It takes positive 357 to break that bond between the C and the H. And this one only takes 354 because it's tertiary allylic, but we don't have a tertiary allylic in our molecule. Positive 357. Remember that number. Positive 357 for both of these. They're both secondary allylic. Okay. Now to make this bond here requires this bond breaking. That is vinyl. I'm not even going to look it up. I'm going to look it up because I'm teaching you how to look things up. But you're never going to pick the one where the halogen is attached to vinyl. The reason is because of this. You're never going to break a 444, which is vinyl. Alkene is a vinyl. 444 does not break before any of these three numbers, 360, 357, 354. And our number that we care about is 357. So I'm going to put plus 44 and cross off another product. And I'll put it plus 444. And that means this one is wrong, which means these are wrong. We're down to 4 versus 6. And question 3 is going to answer why 6 is a little better than 4. And question 3 is thus. This is all for 1 point. It's crazy. Question 3. Which CI happens faster? Remember, you're making this bond. You're not breaking it. All of these were positive. Why? Because you're breaking those bonds. Over here, why are these negative? Like negative 297 for HI, negative 368 for HBr, because you're making those bonds. They're new bonds. We got a secondary allylic. Versus a primary allylic. And when you make it, it's negative. The numbers are, let's go find them. Let's go find them, CI. Here's the allylics. They start here. Primary allylic, secondary allylic. Those are the two numbers. Negative 172 is faster than negative 169. Negative 172 is faster than negative 169. Negative. I forgot the numbers already. It's okay. It's okay. It was 6972. This one was negative 169. This was negative 172. And that one's faster. The more negative the bond forming, the faster it is. We have our answer. Finally. Took forever. Congratulations, we got 1 point. Okay. Now, if you pick the wrong box to circle, you're going to lose a point there. If you use all the right numbers after that point, based on your choice instead of the correct choice, you're not going to lose any more points, okay? We're supposed to provide a mechanism for the initiation. This one has just one initiation and two propagations. So initiation breaks the weakest bond using the heat. And IBR, if you look at the table of all these bonds on these two molecules, every single bond between these two molecules, IBR is the weakest bond by far. So your init starts here. I bonded to BR with the heat. Pops in half. You have to show the hooks, people. Have to show the hooks. Without the hooks, you're losing points. I radical, not very reactive. BR radical, very reactive. You know how I knew that? Up here. I radical picks up an H and forms HI, but it only gives off that much heat. BR radical picks up an H and becomes HBr, gives off a lot more heat. Yeah, it's a lot faster because it BR dot's more reactive. And prop 1, and this one, I can't say it enough times. When you do the two propagation steps, both of them have something in common. Radical from previous reaction reacts with a non-radical. Remember, you have to make HBr from this. So please pick the carbon molecule that has the H's on it. And because I'm doing the product as it's pictured up there, I'm going to do this one. This is another hookup mechanism. Hooks meeting hooks, I call a hookup. Student snicker. It's okay. They're definitely meeting there. The other half of the radical, the other half of the bond goes on the secondary allylic position because it's nice and comfortable with its resonance. We're going to have to show the resonance. Do you know how you have to show resonance in this product, in this molecule, in this reaction? Do you know how you know? The resonance has to be used? I got one simple question for you. Do you see an iodine here in the product you picked? Answer, no. I see the iodine here and there's no radical there. Remember, the halogen goes where the radical is. If the radical is not there, then you need to entertain the resonance possibility. So it hooks in there. This one hooks in to meet it. That's going to be a pi. And this is straight up resonance. We only moved electrons in the molecule. We didn't move any atoms. And you have this radical. Double bonds here now. There's your primary allylic radical. That's the one that forms a bond at the iodine faster. This is going to be prop 2. I'm going to use that radical. Hey, you use the previous radical. Remember what I said the props do? Every time you do a prop step, it's a radical and a non-radical. Well, the radical you made in the previous step is your hint, the radical. The non-radical is the other molecule that doesn't have a radical. That's IBR. And don't try to tell me IBR has been used up in initiation step. Did you just watch the previous segment? Initiation steps use, in theory, just one molecule. Out of a mole of IBR, you've used one molecule. That means you have a whole mole left. You haven't used anything. These two are going to hook up. Watch how similar these hookups look. And you're generating BR radical. Hey, what's the BR radical going to do? It's going to circle back and find another non-radical. Yeah, BR radical is going to circle back and find a second molecule like this. This molecule is our product. So it's done for the day. And if you add up prop 1 and prop 2, you get this reaction. A plus B gives C plus D. HBr was made. I didn't even show it. Oh, doesn't this make HBr? H hooks up with Br. I didn't show it. I will. This guy can be moved and shrunk down a little. Sneak in HBr. We're going to need to see it there when we do our energy calculation. In fact, we're going to do energy calculations in orange. How much energy did it take to break the CH bond? Well, we did the research already. Allylic secondary CH is 357. You put in 357. Why was it putting in? Why was it endothermic? Because in this universe we live in, molecules are held together by bonds. They're not spontaneously falling apart and giving off heat. No, the only way they can fall apart is if you put in heat to destroy them. So, yeah, breaking bonds is endothermic, always. And did we make any bonds in prop 1? That's why it was important for me to show this product here, because you made that bond in prop 1. And when you made the bond HBr, you got 368 kilojoules of energy back. Oh, it doesn't go there. It goes with HBr right there. And delta H prop 1, I'll just call it delta H P1. You just add those numbers. Notice I'm not making you memorize anybody's laws or anything. I'm not going to mention anybody's names right now. No, don't. The only memorizing you're doing is a concept that's a rock solid concept. Breaking is endothermic. Making is exothermic. That's not memorizing. That's knowing chemistry. Okay. And there's no memorizing anything about products and reactants there. Did I say anything about products and reactants? I did not. Breaking here, making there. Positive, negative. Breaking IBR, we haven't researched it yet. But we did research negative 172. Going back to our table for I bonded to BR. It might be backwards on the table. Caution. It might be BRI. That's not going to fool you, is it? BRI. There you go. We're breaking it. So it's positive 179. And delta HP2 is, I didn't even work out P1, did I? I'd lose a point. That's sad. Oh, if you're like me and you got a bigger number being subtracted from smaller, I flip the signs and I subtract the smaller from the bigger. And remember, my answer will have the wrong sign. So 8 minus 7 is a 1. Yes, there's no calculators allowed, everybody. 8 minus a 7 is a 1. 6 minus a 5 is a 1. But you got to switch the sign because 368 is bigger. I need units for your final answers. And delta H reaction, because these two things add up to the overall reaction, you can do this. -4 kilojoules per mole. This is a barely spontaneous process. I would anticipate this would go rather slowly. Okay, so what have we done so far? I think we've done A, B, C. Circled the major. Mechanism, we did our 2 initiation and 2 propagations. We did all of our delta H's necessary. And then we're going to talk about the rate determining step and explain. So of the 2 propagation steps, in a reaction where both propagation steps, prop 1 and 2, this is prop 1, this is prop 2, involve a radical with a non-radical, making a non-radical and a radical. A radical with a non-radical makes a non-radical and a radical. With that in mind, entropy is almost 0 here. Some of you haven't even had entropy introduced in your other classes of chemistry yet. So just please keep in mind, you need to carefully read the discussion in chapter 8. It covers all you need to know there, even if you had no background in entropy. And your answer will reflect the fact that you know that prop 2 will be the rate determining step. And the answer begins thus. This is D. You have to acknowledge first that entropy is not a factor in this reaction. You're trusting your instructor to say this. It's true. Just trust me. And the symbol for entropy is delta S. And for these reactions, it's roughly 0. When delta S is 0, delta G, which is equal to delta H minus T delta S, will be just delta G is roughly delta H. So that gives you permission to use delta H as your sole criteria for determining faster or slower. Remember, the more negative a reaction is, the faster it is. So the faster reaction has the -11. It's more negative. This is slower. It's less negative. In fact, it's not negative at all. It's positive. So when delta S is equal to 0, delta G is roughly delta H. Therefore, the less negative delta H is slower. You can use the short form RDS, rate determining step, okay, which is prop 2. So in the mechanism, if you want to make this reaction go faster, you should focus all of your efforts on improving the outcome for prop 2. Speeding up prop 1 doesn't help you at all. Speeding up prop 2 helps you if you're an engineer working on optimizing reactions, which is one thing engineers do. So that's the answer for D. And we've explained you have to acknowledge this, and this is a conclusion that comes from that, and then interpret your conclusion based on the numbers you calculated in prop 1 and prop 2 for the delta H's. And we're off to the races. D is done. E, how does the rate determining step involved an early or a late transition state? Wow. So prop 2 is this one. There's the reaction. That's a endothermic reaction. E. I'll give you the answer that gives you the full points with the minimum of writing. An endothermic reaction has a TS. Now, that one, you should at least put TS somewhere. And TS is transition state. And rate determining propagation step. I should, if you're going to use the short form, define it somewhere at least once, please. Rate determining step. Okay. Endothermic reaction has a TS whose energy is closer to the energy of the products. Remember, in an endothermic reaction, the products have a higher potential energy than the reactants. And the transition state's always higher than both the reactants and the products. So if you have products higher than reactants, that's going to be closer to the transition state energy. I want to make sure I'm finishing my sentence and stop talking here. TS whose energy is closer to the energy of the products. So don't stop there. So the TS should resemble the products more than the reactants. And what I'm going to do here is these answers are getting the page is getting too tall and you won't be able to read it very well from the starboard notes. So I'm going to just take D and E and move them to a new page. Hopefully it gets everything I want there. I think I got it. X, it's not gone. I got an equal sign that is missing. Yeah, used to be an equal sign. No, now it's an approximately equal. Go back. Random equal sign's gone. And while I'm here, I'm going to copy the mechanism for prop 2. That one, I might have to be very lucky. Yeah, see these things that happen? No, don't do that to me. It's going to grab a lot of incidental stuff. That's what erasers are for. All right, moving that down. So we're only talking about prop 2 because that's what the question asked about. Asking about the transition state being early or late. Now, I didn't quite finish my answer above in red. I'm just having too much fun erasing here, that's all. Use my bigger eraser. Late or early? If you're looking more like the products than the reactants, do the products happen at the beginning or the end? I think the answer is self-explanatory. They happen at the end. Is the end of a reaction early in the reaction or late? Products are at the end of the reaction. So we're talking late here. Do some fancy late here. Boy, oh boy, really. The things we do to make things look nice. Okay, so we need a transition state. And if you haven't read this stuff yet, I really strongly suggest you do that before watching any of the STQA videos. They should be done after reading the textbook, after watching the lectures from previous semester, and then after looking at some of these problems. But late here, and it's a transition state. Transition states, their very name implies they are in transition. Transition between what? Between reactants and products, always. So I need something that looks a little like the reactants and looks a little more like the products. Why? Because this is a late transition state. The symbol for a transition state is always a square box. Now, if I leave it like that, that's not a transition state short form. That's a intermediate. Transition states are much higher energy than intermediates, and they get a telephone pole symbol. Now I have a question for you. In this reaction, let's stick with the word transition. Yes, every reaction is a transition, but what one atom is transitioning from one place to another in this particular propagation step? And the answer to that is the atom iodine. Iodine used to be in this molecule. Now it's on the carbon molecule. Iodine is transitioning between reactants and products. Iodine in a late reaction when it's transitioning will be much closer to this carbon than it is to the bromine where it began. So the carbon that's it's ending up attached to, I'm just going to flip the molecule a little bit, will be quite close to the iodine. And the iodine, just its position is much closer to that carbon than it is to the bromine from where it started. So if you wrote just that on the page, I'd give you 2 out of 3. Now you got to show me you know what the transition is between having no bond at all between iodine and carbon and having a full covalent bond. We already have that kind of symbolism in our minds when we looked at oxymercuration. When we formed that mercury triangle, those were partial bonds. That's the transition between no bond and a full bond. So you show me a partial bond between iodine and carbon and a partial bond between iodine and bromine. Look how late that is. The bromine is almost out of the picture in terms of the iodine. And what part was this one to diagram the transition state? Diagram the transition state. It's F. I know, rather long segment, but it's a rather long question that's worth a lot of points in your test. You'll be having 2 more points than the test when you read about your termination steps. All right, so we have any questions about this page or the previous one?
Nope.
We're good?
Yeah.
All right, so we'll stop that and we'll come back. Any ideas for our next segment? Oh, you mentioned something earlier and I forgot already.
I think it was the section 8.6, yeah, with the NBS.
Oh, see, there's something going on there. Have you noticed every time it shows up on a test, it's a bonus question?
Yeah.
It is, and that will continue. That which means I never give a lecture on that mechanism.
Okay, so that's
I
why
know it seems mean, but I want to see. Bonus means you've gone through extra effort and you understand a reaction. It's actually an intermediate level mechanism. It's kind of higher level than the rest of the course. So I don't want you spending all your time on the bonus, but if you can grasp it on your own, you'll see every answer key's got a full mechanism. I mean, it's not like I don't give you the answer, and they never really change if you look at them. It's just it's not that hard, even though it's a little advanced. But if you stick with it, it's kind of like the hydroboration reaction. I mean, yeah, that was hard, but a lot of you did really well on it because you knew it was coming. So you think of something else when we come back, or let me know right now that we don't need to come back.
I'll take a look.
Okay, so I'll be back. All right, we'll see you very soon.
Yep.
Okay.